Okay, so we're starting our little next section, which is going to be on what's called polar coordinates. So before I actually get too far into this, I want to talk about one thing. So we know our basic coordinate system kind of looks something like this, where we have a positive x, a negative x, a positive y, a negative y, and a point here is made up of an x value and a y value. And if it's over here, it's a negative x, positive y. And if it's down here, we kind of know the deal. So this is the Cartesian plane. And we use rectangular coordinates, meaning we go over and then up. There are many different ways to describe points in space. And this is just the most convenient one for a simple form of algebra. If you guys go on to take calculus in college and you take Calc 3 is when I really learned a lot about different types of coordinate systems. It's very easy to represent some things in some coordinate systems. For example, a straight line is very simple in this coordinate system, whereas in another coordinate system, a circle is very easy, which would then be hard in this coordinate system. We got to go like x squared plus y squared equals 25. That's a circle with radius 5 centered around the origins, looking something like that. That's not the most simple thing, whereas in another coordinate system, a circle is literally just a number. Just r equals 7. There's your circle of 7. So this makes attacking certain problems easier using a different coordinate system. So that's what we're going to talk about today. So this is what's called the polar coordinate system. So polar coordinates are made up of a directed distance r and a directed angle theta. So instead of an x value and a y value, it takes the form of r comma theta, r theta instead of xy. So this is a completely new thing. When you were in 7th grade and you learned what this was, it was very complicated at first. You don't know which one's the x, which one's the y. It's a little bit tricky which one's which. I expect the same slight struggle with this r theta. It's a little bit tricky at first. Now the first step to being able to use these points, these coordinates, are to plot it. All coordinates, or excuse me, all polar coordinates are made up of a distance and an angle. And here's the way I like to do it. We know that in standard form, we have this axis going out to the right. And our angles are measured up or down from this point. So we know pi over 3 is relatively, it's about there. And this 2 just represents a distance. So I'm going to measure up about pi over 3, and I'm going to measure out some distance that I'll call 2. And what this will give me is the point out here, 2 comma pi over 3, meaning I measured up pi over 3, and then I went out 2 from the origin. So, once again, not the easiest thing to do at first. It's quite a bit tricky, but given some time and a little bit to get used to it, should be okay. Looking at 2, I see the only thing that's kind of weird and different is this negative 45. And all that means is instead of measuring my angle upward, as I did in the first, I'm going to measure it downward. And we know 45 degrees makes a angle kind of like this. Let's actually do it in the blue so it's a little consistent. Oops. Like this. So that is of length, we're going to label it 3. And this is negative 45 degrees. Now stuff gets even more weird when I start implementing negative distances. Now we know that distance can't be negative, but what it just basically means is the opposite way. So we're going to start by thinking where positive 1, 3 pi over 4 is going to end up. So I'm going to go ahead and graph that up. So once again, this is our initial point, our initial axis. I'm writing this on a not nice surface, so it keeps messing up. There we go. And 3 pi over 4 we know is going this way. So this dot here would be positive 1, 3 pi over 4. What negative 1 says is instead of going positive 1 out this way, where our angle is, I just go the other way. I go this way. So now, this point here would be negative 1 comma 3 pi over 4. So we'll get some practice with this idea in class, plotting these points, making sure that we know what's going on. Just a quick recap. We're moving around any angle that it gives us, 45, 3 pi over 4, and then we're moving out this r. So this r theta, we're moving the angle first, then I like moving out that direction. If it's negative, it just means we go the opposite way. Now, here's some just little tidbits of information here. If I want to find all the coordinates at one point, because it would be true that if I add 2 pi to any coordinate, you'd end up at the same point. So for example, if I go 1 comma 0, meaning my angle is 0, or 1 comma 2 pi, or 1 comma 4 pi, all of those points would end up being exactly the same, because I'm just rotating 0 times, then 1 time, then 2 times. So, looking here, r comma theta equals r comma theta plus or minus 2 pi n. You can see that is what I did here. But now it gets trickier when I want to go ahead and think about that negative version, and we can think about that negative version. And the idea with the negative is it's essentially half a rotation away. If I make something negative, this here is half a rotation away from this point. It's going half. It's going pi distance away. So another way I could represent this point would be 1 comma 7 pi over 4. So there's going to be multiple representations for different points in this system. So let's go ahead and read what I have written here. So we can make the r negative. We could take our theta and we could add, let's decipher what this means here. So I have pi and 2n. So if I were to multiply this here, I would get 2 pi n. So that's basically one full rotation. And then this 1 multiplied by pi would be pi, meaning a half rotation. So that was getting from this point to this point. I'm going like 180 degrees. I'm going pi radians. So this idea is going to be important to keep in the back of our minds. The next thing is we're going to look at converting between polar and rectangular, because we need to talk about, these different functions, these different points in both coordinate systems. You can see on the left, I have written up a point here. And I've written the coordinate in rectangular coordinates and in polar coordinates. We can see that I go over x, up y, xy, or that I go up theta and out r. So, from this graph, looking at cosine and sine of this angle, we gather that cosine is x over r, and that sine of theta is y over r. From that, we get the following two ideas, that x is equal to r cosine of theta and y is equal to r sine of theta. And these two ideas are going to become very prevalent when we're swapping in between coordinate systems. What else can we gather from the graph is that in all cases, x squared plus y squared is going to equal r squared, and that tangent is equal to y over x, but we should already know these two things. This is a new idea that's going to become very important. And we're kind of going to see what happens in a half a second when we use these. So let's go ahead and use that idea to convert 3 comma 5 pi over 6 to rectangular. So this is a polar coordinate right here. I have r comma theta. I got a distance 3 and an angle 5 pi over 6. So what I'm going to do is I'm going to use the fact that x is equal to r cosine of theta and y is equal to r sine of theta, which we just found using this picture up here, to go ahead and solve. So my r is 3 and cosine of 5 pi over 6. And I know that 5 pi over 6 is negative root 3 over 2. And if I were to type this into a calculator, I'd get about 2.6, negative 2.6, I should say. So that's my x value, and my y value being 3 sine of 5 pi over 6. I know that that is going to equal to 3 times positive 1/2. So I'm going to get 1.5. So my xy coordinate is going to equal negative 2.6 comma 1.5. So once again, all I did is I used this r cosine and r sine of theta to relate to x and y and go ahead and plug in my radius or my distance and that angle into these formulas. So that's going from polar to rectangular. What if I want to convert an xy, let's just write that down, an x comma y into polar coordinates? So we got a slightly different way we want to do this. So I need to get r and I need to get theta. So this is going to be a little bit more difficult to think about, just to keep it simple. So let's just go ahead and draw up kind of what this is looking like. So negative 1 comma 1 appears in this quadrant over here. So in order to find this distance, r, we're going to go ahead and use that formula for essentially the Pythagorean theorem that x squared plus y squared equals r squared. And both x and y squared, I'm going to square negative 1, and r squared. So that's just taking these 2 points, plugging it in here, and I solve. So it's 1 plus 1, r squared. So when I do this out, I'm going to get plus or minus root 2 as r. And we're going to have to think about that plus or minus in a half second. Now, how I get the angle here, or better thought of as here, is I'm going to use that tangent idea. So tangent of theta equals y over x, which is going to equal 1 over negative 1. Now, using this idea, I could take the inverse tangent of both sides. And I think about the two spots where tangent is equal to negative 1, which I know would be at these two spots. So theta is going to equal to pi over 4 plus or minus 2 pi n, or 5 pi over 4 plus or minus 2 pi n. Now, we have a few different things that we can do now. I need to think of how I would represent this. So I know that this angle, not pi over 4, excuse me. This would be 3 pi over 4 and 7 pi over 4. There we go. How do I represent this angle? I know that would be 3 pi over 4. And then what would my radius be if I go over and then out in that direction? It would be the positive version. So one of my answers would be something like this. It would be root 2 and then 3 pi over 4. Now, how would I write that as an equivalent using the other two ideas, this minus idea? Well, this is going to go back to that idea here, where if I have the negative r, I'm essentially going to rotate it halfway around. So I could rewrite this as negative root 2 being one of my answers over here. And I can add or subtract pi. In this case, we could subtract pi to get pi over 4. Or in the same line of thinking, we could go negative root 2 and do 7 pi over 4. All of these represent the same exact point. It represents this point. It's a little bit tricky to get your head around the fact that more than one things can equal more than one things. Or this point can be represented in more than one ways. So, now that we got kind of this conversion out of the way, and we're going to do more of this, don't worry, let's look at what happens if I want to convert a whole entire equation. So here I got this equation in polar, and I want to convert it into something in rectangular. So I'm going to tell you right now, this is a circle. This is a circle, and we'll kind of show that. The first thing that I want to do is I want to get r and theta into x and y. So I'm going to use these three functions to go ahead and do that. And looking at this, I don't really have, I don't have r times cosine anywhere. I just got normal cosine. And I don't have r squared. So what I'm going to do is this clever little trick where I'm going to multiply both sides by r. What's going to pop up is r squared equals 4r cosine of theta. Now, I got r squared. I could put that in terms of x and y's. And I got r cosine, and I could put that in terms of x. So I could do x squared plus y squared equals 4 times x. 4 times x. Now, what else could I do in this case? I can bring over that 4x. So I'm going to get x squared minus 4x plus y squared equals 0. Now, we're going to have to use this clever little trick. So this is the equation of a circle. It's x minus h squared plus y minus k squared equals r squared, being the radius of the circle. So right now it's saying, oh, I got a radius of 0. That's not really going to work out. So I left a space by this 4x because if I add 4 to both sides, I'm going to be able to factor this into something that looks more like that. So, essentially, factoring that, we can rewrite that x squared minus 4x plus 4 as x minus 2 squared plus y squared equals 4. So this would be our equation. Now, I know that this is sort of a higher level example. The next one's going to be much, much simpler. This is sort of a higher level example of how you would use this, but we could see this complicated function where it'd be really hard to get y by itself is expressed much simpler in polar coordinates as that. So this is a circle, and it's just basically shifted to the right 2, and it has a radius of 2 given this. And this is just a much simpler way to express that. Looking at this one, this r equals 4 secant of theta, we're going to look at Desmos of what this is and why we're using this one as an example specifically. But we don't like secant because this is in cosine and sine. So what I'm going to do is I'm just going to real quick change this to 4 over cosine of theta. And then I could see if I multiply cosine onto the other side, I can rewrite it as r cosine of theta. R cosine of theta equals 4, and r cosine of theta equals exactly x. So x is equal to 4. So this function here is really just a straight line. And we could see x equals 4. We know what that looks like. If we have a y-axis, it looks like this. It's going straight up. So let's pop into this. And Desmos has the ability to use polar coordinates. So I've typed in our function up in the top left. And we could see that we get this straight line happening. So straight lines are actually harder to deal with in polar coordinates, but it's easier to deal with circles. as we saw here and here. So this is a vertical line. And the last thing we're going to look at today is, hey, what if we go the other way? Oh, this is the stuff from the beginning. What if we go the other way? What if we go rectangular to polar? What would we do then? So we got a little bit of a different approach to this. So what I want to do is I'm going to go ahead and FOIL all this stuff out. So what I'm going to get is x squared minus 6x plus 9. This is just going to make it easier to deal with. And then still equal to 13. And with some regrouping and moving things onto certain sides, we could see that if I subtract 9 and subtract 4, I'm going to get 0 on the right. And then I'm going to group my x squared and y squared together, because in the next step I'm going to go ahead and simplify that in a nice way. So I'm going to be left with negative 6 x minus 4y. And I want to bring it into polar, so I'm actually going to grab my little ideas that I want to follow. Much like we did when we were verifying and solving for trig stuff, we got some ideas that we want to follow. So if I see x squared plus y squared, I could replace that with r squared. So I could replace this with this. My whole goal is to get everything in terms of r squared and r and theta. And I don't want x's anymore. So now I could get x and use this r cosine. So I'll get negative 6r cosine of theta. And then lastly, I could change that y into negative 4r sine of theta. So we could just review really quickly what we did and what our goal was. So I say our goal is this. We could do a double arrow. So it's to get it from x or y to r and theta in this case. Looking at common factors here, I could just go ahead and pull out a r. So we're going to do that. I get r, and then r minus 6 cosine of theta minus 4 sine of theta equals 0. Dividing both sides by r, because essentially, if I were to set r equal to 0, which we can do because this is multiplying here, r equals 0, that just means we're sitting on the origin, and that's already part of this function. So we can divide both sides by r and almost ignore it. We can fulfill our idea of getting r by itself, because that's what the form these polar coordinates take. So r is equal to 6 cosine of theta plus 4 sine of theta. So this is a much simpler way to go ahead and write this equation. Even though they're different variables, I have an equation in terms of one variable, and up here I have an equation in terms of two variables. So just a really quick brief, this is not the easiest topic, but it's also not the largest topic within the AP test or AP exam. So we're going to spend a couple more days on this. We're going to look at a few different types of functions that pop up. We're going to look at a little bit of symmetry, and then we're going to look at some AP questions. Once again, these are difficult topics. I promise, with every fiber of my being, once we get out of trig, it's going to get much, much, much simpler. There's not going to be all this crazy math and swapping coordinate systems and all this fun stuff. But this idea behind polar coordinates is actually really cool, and it's a little bit eye-opening in the way that we are able to do math in different ways. So, with that being said, we're going to go ahead and practice with this tomorrow. Have a good rest of your night.